So today we are going to move to a new section on the array level design. So far we talked about the individual memory technologies from the mainstream technology like SRAM, DRAM, flash, and emerging technologies like those RRAM phase change or the STT run. So here we are going to talk about some of the array level design considerations, especially on the peripheral circuits. So this is outline. So we'll talk about one subarray and then the peripheral circuits, and then talk about some higher level band localization, and finally we will have a tutorial to this MV scene simulator, which you are going to use for your homework 5. So this is a generic subarray for the memories, and no matter which memory, you may have those blocks. And here, the green part is a 2D array of memory cells, like your SRAM, DRAM, or this 1T1R or crossbar. So then, at the edge of the array, you may have those peripheral circuits, like the decoders, MUX, sense amps, drivers. Sometimes you may have the precharge and the equalization. So here we are going to look at those individual blocks in more details. You may have seen some of them in the previous discussions in like SRAM or DRAM. So first of all, let's look at the decoder. So you need to use decoder because you have the address to decode the individual rows or the columns of the memory array. So decoder, is a standard logic circuits, and you have the input address, and then you have n bits. Then you're going to decode that to the power n output. So this is a simple logic, and this is the input and output relationship. And then of course you can synthesize this using standard logic rules. And here, this is a very simple example for the 2-bit decoder. Let's say your input has 2 bits. So basically, this first bit and second bit. And of course, you have the complementary signals for those, like 1 and 0 for each bit. So you're going to decode into 4 rows, for example, 4 word lines. So a simple logic is just like this. And you can simplify it if you implement transistors. So here, you can just use the pull-down network, MOS, to do this job. And then you just need a common PMOS for the pull-up. This is just to save the, let's say, save the area. Ideally, if you use CMOS technology, then CMOS, let's say CMOS circuitry, then the pull-up, you will have 4 PMOS in stack, right? If it's a 4-input NAND gate, then you are going to have 4 PMOS stacking up. Here, for the memory circuits, you want to save the area, so you can just use 1 PMOS always on as a node to the pull-down MOS network. So this is static logic. And of course, you can do the dynamic logic if you care about the speed. So then you can have this pre-charge signal to this PMOS, and then you can use dynamic logic to do this. So I will not go into the details. I hope that you know this through the advanced VLSI, those kind of courses. So this is just a quick summary on the decoder. And one thing is that sometimes your memory array is very large, like 1,000 by 1,000. That means 1024. You need 10 bits to decode, right? So 10 bits for 1024 rows. Then the challenge is that it's very hard to have such large fan-in, right? You have 10 input bits, so it's really hard to design a 10 input NAND gate, right? So it's almost impractical. Therefore, it's better to split this into two stages. So this is like two-stage decoder. For example, this is let's say 4 bits. You need to decode to 16 outputs. And what you can do is to divide this into two stages. The first stage is 2 to 4 bits, 2 bit to 4 outputs decoding, and then you have the second stage do another 2 to 4 decoding. So you break up this into two stages, and then you can save the area because the fan-in now is reduced. So typically, if your address bit is larger than 5 bits, then you want to do this two-stage decoder. So after the decoder, then you will drive this Wordline, which may be a very long wire. So to drive the wire, which means you are driving some capacitance, right? So to meet the timing, then you need to have some kind of drivers to send in this signal, because this wire will be very long, and we know the wire will contribute to this cap, parasitic cap. So we may need this kind of driver followed by this decoder to drive this long wire. And you know, driver essentially is what? From your digital circuit courses. What makes driver?
Chain.
Inverter chains, right? So here you have this inverter chain to drive a large capacitance, essentially, to reduce the latency and meet your timing requirements. And here you can have different kinds of options to design the driver, depending on your targets for optimization. So if you want to really shorten your latency, then you need to break up this into multiple stages. And there's an optimal number of stages using that so-called what? There's a law, right? I remember in the digital circuit. I think you may have learned that. So there's an optimal number of stages and an optimal size for each stage, given the, let's say, input and output capacitance ratio. So in this example, you can break up this into, if eventually you are going to drive this kind of capacitance. Let's say this capacitance is normalized to the unit capacitance by one inverter. If your final capacitance is like 4,000 unit capacitance of one inverter, then you break up into this kind of few stages, and with increasing size of the inverter for each stage. So this is, you can see this is W/L ratio for the NMOS. So if you do this example will tell you a total delay from here to here will be like a 30 unit cycle. One cycle is defined as the latency for one inverter with the minimal size. This is the unit cycle. And if you do this kind of inverter chain, then you will minimize the total delay to be 30 unit cycle. And the total area you need to pay for this, you need to add up those area, will be like 1,300 unit area. One unit area is the area of one inverter with a minimal size. So this gives you the best latency, but of course the area will be very large. Then you can have area optimized design where you try to just minimize the number of stage. And if you just do this 2 stage, you just will have a large buffer here. Then the area is just 1 plus 64 is 65. But the latency here will be 130 unit cycle. You see the trade-off between the latency and the area. Of course, then you can have a balanced design like this. Then you try to balance the delay. If 80 is between this 30 and 130, and the area actually is a little bit larger than the minimal area, but it's much smaller than this one. So maybe this balanced design is what you want. Of course, depending on your application, right? So you are designing the cache, or you are designing like flash, then it's very different, right? So if you are designing like SRAM cache, you care about the latency, right? Then you want to optimize the latency. But if you are designing like DRAM or let's say the NAND flash, then you care about the density, right? Area is important, but the latency can be slower because NAND is slow anyway, right? So you need to consider your application to design those peripheral circuits. Any question? So this is from the row side, and now let's look at the column side. So the column side, at the end of the column, we may have this Bitline MUX to select which column you are going to read out to the sensor. So there are 2 kinds of column MUX. The first one is quite commonly used. Is the pre-decoder based. This one. So essentially, this one is you have a column decoder here to decode the column address. For example, in this simple example, you have 2-bit input, 2-bit address for the column, and then you decode to 4 columns, right? 4 columns. So from this decoder, you have 2-bit input and 4-bit output. So those 4-bit outputs will serve as the control signal to a pass gate, or sometimes you can use the CMOS transmission gate, which transmission gate is a pair of NMOS and PMOS pass gate. But you can just use one pass gate; it's fine. So here you have 2 of them because they are like a Bitline bar for the differential sensing. So you need to select both at the same time. So here you can use this to decode the multiple columns. First, decode the address through a column decoder, and then the output from that decoder control the gate of the pass gate. The pass gate, you need a pass gate for each column. And the other design is to, let's say, get rid of this column decoder. So you directly use input as the address here, and then the MUX actually is a tree-based MUX. So here you will have those transmission gates, have this kind of topology. So basically it's like a tree. You first select which branch you want to go, and then you have this kind of node and leaf, and then you will decode to the individual branch, which is the column. Here. So this way you get rid of the decoder, but this one is not commonly used. Why is that? Any idea? I would say the left one is more widely used.
or PMOS here?
Your series path resistance.
Yes, exactly. So if you look at the next one, this is just a 2-bit, which is a toy model. In reality, you may have 6-bit, 8-bit, even 10-bit, right? So this one, no matter how many colons, how many colon address bits, then from the colon to the sense we just go through one passgate. But for the right one, this tree-based one, if you have 2 bits, you go through 2 passgate to the sense amp. If you have 3 bits, you go through 3. If you have 5, you go through 5. Then this series resistance along that path will be too long for the sensing. So which is not good. Okay, so this is colon side, end of the colon, and then let's look at how we do the sensing. So essentially we need to model this bitline, because this bitline goes to your sense amp. And we can have this kind of abstraction for the bitline. So essentially you have your memory cell, and then the memory cell will go through the bitline and to your sense amp. So because bitline is kind of long, then we need to have this resistor and the capacitor network to model the bitline. You cannot lump the resistance and the capacitance into just a single resistor or capacitor. So here we try to model this your memory cell as some current source with some memory cell resistance. Of course, you can use other equivalent circuit. It's the same thing, right? So let's say this RB is the memory cell resistance. So here the equivalent, if this is like what? Any idea? Undergrad circuit.
Right. Oh.
Here, if you want to make those two as equivalent circuit,
Thevenin and Norton.
so you have voltage source here, right? So this is you simply model the memory cell, and then you have this bitline, which is a distributed RC network. Each segment you have the wire resistance, and each segment you have the wire cap. And then at the end of the column, you will go to your sense amp here. So sense amp, we just need to use input in resistance to model your sense amp. It's like input impedance. If you look into your sense amp, you will see that input resistance. So you need resistance to model the sense amp. So this is a very simplified model. And from this model, what do we want to derive? So we want to derive the latency. So if you have signal from here and then pass through the RC network, so then your signal, either voltage or current, will be transmitted to the sense amp, which detects the small difference in the voltage or in the current, and then the sense amp will convert that to the digital 1 and 0. So we want to understand the delay from the memory cell to the sense amp. So what is the delay? So here we have this notation. This RB is for the memory cell, and we have the RT and CT, which is the sum of all the wire, let's say R wire and C wire. So the RT is the total the sum of the R wire, and the CT is the sum of C wire. And then this sense amp input resistance is RL because it's like a load to this network. Okay, so if we have those parameters, then this is a delay. So if you really solve this network using the RC equations, then you will get this kind of formula. So this is a delta T, and you can see it depends on this total R wire and C wire, the total wire cap resistance, and also depends on the memory cell resistance and the sense amp input resistance. So it's this formula, okay. And it's kind of complicated, but we are going to simplify this in the following slides. Because this relates to how you sense your signal. You sense it as voltage or as current will make a difference here. So for the sense amp, in general, you have two kind of sensing scheme. One is the voltage sensing, one is current sensing. So depending on how you sense it. So let's look at the voltage sensing first. If your sense amp senses the voltage signal, what does that mean? Any idea? If your sense amp, right, your memory cell and then travel through the wire and then go to your sense amp. And if this senses the voltage, what does this mean? So if you read this, it says that if you sense the voltage, it's like this is the input resistance is infinity. And this is like open circuit. If you look into the sense amp from here, because ideally when you measure voltage, if you think about the voltage meter, right? If you measure voltage, you have something in parallel with your device to be test, device under test. You have voltage meter in parallel with that, and that voltage meter, the input will take no current. It will not take any current in. So it's like the resistance is very, very large, and it's like an open circuit. So if RL is infinity, then you look at this equation and you can simplify it, because infinity here, this is like two very large number. So you have some difference here, but overall it's like two large number. You have one large number divided by the same large number, so you will get what? 1. Right. And then this is the same thing, so you will get 1. Then you can combine those two and then you get the delay like this. If it is the voltage sensing, okay. If your sense amp is ideal, or let's say this voltage mode sensing with ideal input resistance very, very large, then you get this delay. On the other hand, for the current sensing, so what do you assume? For the current, your memory cell and then go through the wire and then sense amp, you get current in. So what does that mean? This current needs to flow somewhere, right? Yes. So ideally, that will be ground. Your current will go to the ground directly. It's like there is a short circuit as input for the sense amp. So that means the input resistance ideally is 0 or very small. So this is when you sense the current. Right? Because when you measure current, you need to use a current meter in series with the, let's say, the path where you read the signal. So this is how you sense the current. So you can plug in 0 for the RL. Then if you do that, then you can derive this to be in this. So this is the delay if this is the current sensing.